So when we look at the octet, this is octet, octet, octet. So that's good. But we should also look at what? We always look at octet and formal charge. So what's the formal charge on this N nitrogen here?
-1.
Yeah, 2, 4, 6, -1. This middle nitrogen?
+1.
+1. And this oxygen?
0.
0. So that seems pretty good. You know, compared to +2 on oxygen, a 0 on oxygen is going to be a lot happier. So I like that structure better than this structure already. You know, this one should be more stable. Did anybody get any alternative structure for this? Well, one alternative structure is, you know, one way to reduce the formal charge? I should have tried it here, but I didn't. But I'll try it here. I'm going to try to get all zeros here. I'm going to try to get all zeros by making a triple bond here. So if we do it like this, we go N triple bond, N double bond O. What would the formal charges here be?
0, 0, 0.
Yeah, now if I counted 2, 3, 4, 5, that's 0. 1, 2, 3, 4, 5, that's 0. 1, 2, 3, 4, 5, 6, that's 0. And then that's, we have a structure with minimized formal charge.
But it has 10.
Yeah, but the problem is the nitrogen here. It has 2, 4, 6, 8, 10 electrons. How many electrons fit into the second shell? 8. So the second shell can fit 8 electrons max. 8 electrons is the octet. So the 2 extra electrons must go into the third shell. So 2 extra must go into the third shell. Is that energetically favorable? No. It turns out it's too much energy. This is too costly. So it doesn't happen. And so we come up with another rule to help us with Lewis structures. The other rule is that second period elements, or second shell elements, never exceed an octet. Never exceed an octet. And so this structure is no good. This one we could have minimized the formal charge, but we would have made way too many bonds for this one. The triple. And so this looks pretty good, except, did anybody get another structure for this? The other structure for this is N triple bond N single bond O. 3 lone pairs on the O, 1 lone pair on the N. When we look at the formal charges here, this N nitrogen has 0, and this middle nitrogen has 1 plus, and the oxygen has minus. So between these two structures, the middle nitrogen doesn't change. The only difference between these two structures is we have an extra electron on nitrogen or we have an extra electron on oxygen. Which one do you think prefers the extra electron, nitrogen or oxygen? Oxygen. Oxygen prefers the extra electron. But how much more does it prefer? And so if we look at the electronegativity of oxygen versus nitrogen, nitrogen is a 3.0, oxygen is 3.5. And so it's not a huge difference. Nitrogen's pretty strong. If nitrogen and oxygen got in a tug of war, there'd be a fight. Since there's a fight here, what we see is that both these structures exist. However, this one is going to be more preferred. So this is called resonance here, but this is unequal resonance structures. So I'm not going to draw a symmetric double-headed arrow. I'm going to draw kind of an asymmetric one that favors this one. We could use quantum mechanics to see how much this one's favored. Maybe it's like 80% this one, you know, this is and not 50-50, maybe it's 30% more stable than this one. This might be 20%, you know, to give us 100% of it. This is just some guess. But we'll talk more about this next time. But it turns out this is the most stable structure here. But it's not a huge difference because both nitrogen and oxygen are quite electronegative. Stop here.